Now we're going to see the first of the Maxwell equations in terms of derivative instead of integral form, and to see why the electric field is the negative of the gradient of the voltage. So we have here a charge Q1, another charge Q2. The force between them is Coulomb's constant times Q1 times Q2 divided by the distance between them squared. K is also equal to 1 over 4 3 epsilon naught. The work that is done could be from attracting them if they have both the same charge, so from bringing this charge from here to here, or if they have opposite sign would be the work done from bringing this charge from here to here. The work would be the integral of the force dot dl. The units here are joules, here we have Newton, and here we have meter, so the units would be also joules. Now if we divide everything by charge, so by Q, we know that force divided by charge is the electric field. This is the electric field. And here by the unit, we know that joules divided by Coulomb is volt. So we would have that the voltage is equal to the integral of the electric field dot dl. Actually, if we are talking about a conservative field, that means that the work done in a closed loop, so could be from bringing this charge here and then here, 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 and returning to the same point. That means that the work done would be equal to 0. So in this case, if we divide everything by Q, we have that the closed loop of the electric field dot dl would be equal to 0. Only if we have a conservative field. So now, if we want to check that the voltage be equal to this, we know here that the electric field is Coulomb's constant times Q1 divided by R squared. Here, because we have that the voltage is equal to the integral of E dot dl. The dot just means that we are putting the L in the same direction than E, so could be times the cosine. So this is the same as saying that the electric field is equal to the derivative of the voltage, but instead of writing just dB in dt, we need to take the dB in dx. We need to put this symbol nabla or del. That means that we are taking the derivative in the x, y, and z components, because the electric field is a vector. The electric field could have some component in x, y, and z, or could be that all the electric field is in the x direction and 0 in y and z direction, but anyway it is a vector. So we say that the electric field is equal to the derivative of the voltage, meaning in the x, y, and z direction. So instead of saying the derivative in all that direction, we say nabla, where nabla is the vector partial derivative in the x, partial derivative in the y, and partial derivative in the z. If we apply this operator to the voltage, then we would have that the gradient of V, when we have the nabla operator times a scalar field. This is, say, the gradient. That means the steepest change in the direction because the derivative is like the change in direction, like a slope. The greatest change in the direction is the gradient, and this would be partial derivative of the voltage in dx in the I direction or in the x direction, plus partial derivative of v in the y direction, in the j direction or in the j direction, that is the same, plus the partial derivative of the voltage with respect to the c direction in the k direction or in the c direction. You can write it as this or as a vector. This the vector you can write it as this, putting I, j and k, or in this vertical form, that would be dv in the x, dv in the y, over partial, and partial dv in the c. Alright, so we have here that the electric field will be equal to the gradient of the voltage. So now we need to take the derivative of the voltage with respect to the distance. So here we have that work is equal to force dot dn, and in some videos ago we noticed that this work, in that video we put potential energy, that the electrical potential energy was converted into work and then kinetic energy, but that was the negative of Coulomb constant times Q1 times Q2 divided by R. This was the electrical potential energy. So if now we divide that by Q2, then we have that the voltage here, the voltage is the negative of Coulomb constant times Q1 divided by R. And we had, oh, I already erased it. Well, we said that the electric field was K times Q1 divided by R squared. Let's take the derivative of the vector of the voltage. So the gradient, I will take it in the R direction, that the R direction has the component in X, Y, and Z. So in this case I could say dV in dr. This would be equal to, I can take these two constant out, so minus K Q1 times the derivative of 1 over R with respect to R. So the gradient of the voltage would be equal to this 1 over R is the same as R to the negative 1. So the derivative would be minus 1, this goes here, so minus times minus would be positive, K Q1, R to the negative 2. So it would be K Q1 divided by R squared. So this is because in the voltage here we take this work or electrical potential energy that is with this minus here. If we would just have take that the voltage, because when we're talking about voltage, we just say K times Q1 divided by R. When we take the derivative, we would just have minus K Q1 divided by R squared. But we have that the electric field is K Q1 divided by R squared. That is what we got here, not here. So actually the gradient of the voltage is this. This here, when we put this negative sign here, this we are taking the negative of the gradient of the voltage. So actually the electric field is equal to the negative of the gradient of the voltage. We can write it like this, so minus here, and this would be equal to the electric